Alright, so the last thing we want to prove about the characters in the inner product is that the characters form an orthonormal basis. So given the irreducible characters, the set of all irreducible characters, we'll call this IR of G, this set. We need to show that this is a basis for the ring of class functions, or the vector space of class functions of G. And remember, the reason why we do this is because it allows us to conclude that the number of irreducible characters is the number of conjugacy classes of the group. So there's an advantage to doing this approach. So the set of lecture notes in section 3 points out it's a consequence of Wedderburn's theorem, which we're skipping because that uses a lot of stuff from algebra and module theory. So we need a different proof, but it turns out there is a self-contained proof. It essentially is proving a special case of Wedderburn's theorem, but we're going to do it, so let's go ahead and do it. So here we go. Let's do this proof. So what we have seen is that the irreducible characters do in fact form class functions. So their span is a subspace. By the way, all characters are in this span, as we've seen from the last lecture. And so we can let W be V perp, which, if you remember, would be those class functions with the property that the inner product with F and alpha is 0 for all alpha in V. This is called the complement, normal complement of V. So this is something you can do for any inner product. It's the perpendicular subspace, so to speak. And this thing is normally important when you're trying to study the Gram-Schmidt orthogonalization process. It's how you try to get from a basis to an orthonormal basis in linear algebra. But the point is, this is a thing that exists, and what we want to claim, so a fact that we need to know is that in general, for any inner product space, if you have a subspace, the overall vector space is equal to the direct sum of that subspace and its perpendicular subspace. That's one reason why we study it, perpendicular subspaces. So all we need to show is that W is 0. If that's true, then V is all of W, and therefore we already showed that these characters last time had the feature that their inner product was either 0 or 1, which is enough using the theory of the theory of inner products to conclude that they are linearly independent. And so they're linear independent vectors in their span, so they're a basis of their span. If this is the 0 subspace, the set of class functions is this span, and therefore they form an actual basis. So let's take something in here. So now what do we know? We know that the inner product of F with any one of these things is 0. In particular, what that means is for any G module V, if you take the character associated to it, And then product of f and that character has to be 0. In particular, if you take any of the irreducible representations, you're going to get the inner product to be 0. Remember that this means that you're looking at the dimension of a Hom space. But let's actually tease out exactly what that means, and specifically. So we're going to prove a preliminary lemma in the middle here. So we're dealing with the class function. And V is a G module. Then what we want to claim is that the linear operator given by doing the average, where now you multiply by f of v. Well, I'll do the conjugate. F of g dot g under this action is G invariant. Which would mean, of course, that it actually is an element in Hom VG. But let's look at this claim real quick. So why should it be true? Well, let's see what happens when you act by a group element. Let's call the group element H for now. H dot V. We want to be able to pull the H out entirely. Got H all the way on the inside. H of V here. The clever way to do this is to cleverly multiply by H inverse in the right spot. Remember, FG bar is in fact a number. Here we're dealing with the group action, so I can replace G of HV with GHV. We can bring this H inverse past the scalar, and we get H inverse here. So it looks like we're replacing G with its conjugate again. But that substitution might seem weird here, except we remember that we're constant on conjugacy classes because we're dealing with a class function. So when I do the substitution, replace G with H inverse GH, I can take advantage of the fact that FG is equal to FH inverse GH here. And so I'm guaranteed that after I do this substitution, or change of summation, these coefficients are the same. And so I do in fact get H times LFV. So this is G invariant. Now let's use that lemma. Let's look at f with respect to xi. This is 0. What is it? That's the trace of this linear operator we just had. Now remember, we're dealing with something that is G invariant. And so by Schur's lemma, this transformation, so this is just the trace of LG VI, or VI I should say. Not G, that should be F. VI. By Schur's lemma, because we're looking at an irreducible representation, G module with itself, this map has to be a scalar times the identity transformation, which has trace lambda. So what is lambda? Lambda is 0. This is a 0 map. And this is true for all irreducibles. So we've seen what happens. We got information about when we take the inner product with this class function with any irreducible representation. The fact that it's 0 says that this crazy summation is 0. It tells you that this trace of this linear operator is always 0. Now we're going to work with a different representation. G acts on itself by left multiplication. This gives rise to a famous representation called the regular representation. I'm going to go ahead and let chi be the character. Chi rho. On one hand, that's the trace of this construction. So here the proof is going to get kind of hand wavy, but this is correct, since we know that you can decompose the regular representation into these irreducibles in a precise way. That means you can find the right basis, that you can split this summation up right. And so the whole point is that you can rewrite our linear operator in terms of each of these bases. As a linear operator restricted to each basis. Let me make that more precise. So what does L of FV look like? Well, currently it should look like 1 over G, summation over G, F of G bar, V of G. Now what happens when you use the standard basis? Well, then the elements of G are linearly independent. And from this information and with the dimension considerations, you can actually calculate and figure out what the class function was. So it is possible to derive the class function from this basis. And you should try to write down that formula sometime. It's kind of interesting, but it is possible. So it's possible to deduce the class function uniquely from this formula. The next step you have to show is that this class function is identically 0. And how do we do that? Well, we need a different basis. you now choose the basis so that phi of G is diagonal, or well, splits up into its irreducibles. We know from Maschke's theorem such a basis exists. Why do we want such a thing? Because then when we're doing this calculation, what does LFV look like? 1 over, well, it's a bunch of block matrices. Each one of these actually looks like LFVI, essentially. But as we just saw, those are all zero matrices, so this is a zero matrix, which means that this is also the zero transformation. And so as long as you believe this claim, that from the standard basis you can compute the class function, it follows that this class function has to be zero, which is what we wanted to show. So there's one little gap we would need to fill. But modulo that gap, you can actually prove that this is a basis, given by the irreducible characters. Or you just fill the gap by realizing if you've got the zero map with respect to some basis, it's the zero map with respect to any basis. And because these are linearly independent, it must be the case that this is in fact the zero vector. So congratulations, we have an orthogonal basis for characters. It's worth pointing out, this actually does allow you to get a second orthogonality relation. From the fact that if you've got a matrix where any two rows are orthogonal, then any two columns are as well. So here the idea is that you're going to replace your original inner product with the slight version. It's equivalent, but what you're choosing is representatives in each conjugacy class instead. And why would you do such a thing? Well, it's the same inner product, but then you got this theorem from linear algebra that tells you any two columns have the same. If every two rows of the matrix are orthogonal and your matrix has just as many rows as columns, then any two columns are orthogonal as well, and vice versa. So in particular, any two columns in our matrix, or since we already know any two rows are orthogonal because our rows correspond to characters, we now know any two columns are. And what do the columns correspond to? Well, the columns were chi I g j for a fixed group element and the characters varying. And so what happens when you take the inner product of two columns? Well, you've got two different group elements, but the same character. Multiplying by the conjugacy class just means we should be multiplying by the conjugacy class of one of them or both of them, but we'll ignore that and ignore the G for right now. you're either going to get 0 when G and H are not conjugate, or otherwise it turns out you're going to get the size of G divided by the size of the conjugacy class of G. This thing is also known as the size of the centralizer, as we've seen before. It's worth pointing out from this information, you can actually calculate the sizes of the conjugacy classes from the character table without knowing it in advance. So just given the entries in the rows and the columns, without the labels of the conjugacy classes, you can calculate the sizes. So that's a nice feature of the character table. And for larger character tables, when you haven't filled in all the information, this allows you to calculate some other stuff too. The notes mention at least one other fact that I thought was kind of interesting that I'll end with while talking about character tables, is if you have a normal subgroup, well, if you have any subgroup of G, then H is normal if and only if it is of the form elements in the group with the feature that a character value at that group element is equal to that character value at the identity element for a bunch of characters in some fixed subset of irreducibles. So the point is, one way to find normal subgroups is to take subgroups and check the normality condition. Another way is to take subsets of irreducible characters and generate this set Si to be those group elements with the feature that the character value of each irreducible character on that group element is the dimension of that character. This subset is not necessarily a subgroup. Of course, since this is a class function, this is closed under conjugation. So you're taking unions of these types of conjugacy classes, and the ones that are actually closed under multiplication and inversion, those are actual normal subgroups. And every normal subgroup arises in this way. So a group that has very few irreducible representations, this is a nice way to find the normal subgroups.